So what I want to talk about is a separate video focused on the moment of inertia because it's important in the second half of the course. And to a certain extent, you're already familiar with this. You've done problems with moment of inertia in Civ 100, the statics course. But it's useful to focus in on what exactly you're doing and the tiny differences that will exist in this course. Discussions about calculate moment of inertia, and just a point, there is another sort of overview lecture that I have which talks about the parallel axis theorem, radius of gyration, and how these are derived. But this is not that lecture. This is more focused in on the volumes and the mass. So angular acceleration about the axis AA prime. So you have AA prime over here. Duck, duck. For a small mass, and that's just the mass over here, delta m, is due to the application of a couple is proportional to r squared, the distance, the perpendicular distance from AA prime to that mass element. And so if I want to know the moment of inertia of the mass delta m, it's going to be r squared delta m in this case. And you can kind of see this is going to be related to the mass of gyration. So it's as if I put all of the mass a uniform distance away, but it's only for a small elemental mass here. And if I have a body, then I can add up each of those individual masses. So I have R1 delta M1, I have R2 delta M2, and I create this summation over the entire body and then integrate it, which is sort of an addition process, r squared dm, and I get the mass moment of inertia. And going back to this radius of gyration for the entire body, I can say I is equal to k squared m, where I pretend all of the mass of the body has now been shifted to a disk or a shell, a uniform distance k away from this thing, k from the axis, excuse me. So you have here a pretty good way of describing things, and that's sort of where we sort of rush through this part of the conceptual discussion. But if you continue more, you can sort of say, look, I've got a mass, and here's sort of some arbitrary red line that defines a uniform material or uniform body of some sort with individual masses that are dm. So along with this axis, I've got x, y, and z here. Distance here is x, distance here is z, here distance here is y. And the distance from that origin is a total distance of r. So it's just the square along the xz axis. So if I'm looking about the integration about y, the distance of this body, the perpendicular distance, is going to be r squared dm, or z squared plus x squared dm. And for the other two, it's going to be y squared plus z squared, or x squared plus y squared. So it's, and then you integrate over all of those distances. And you can see immediately, and this is something that's been emphasized in the lectures, that moment of inertia is not a constant value. It depends on your axes. It depends on your location. So in all likelihood, Iy, Ix, Iz are all going to be different dependent upon the case you're looking at. Big thing here is what the units are, kilogram meter squared. And for laughs and giggles, always US customary units, slugs, pound mass, and all sorts of, and pound forces. It's good to know what it is and be aware of it. If you do use US customary units, I do strongly recommend using slug feet squared, not pound mass, pound forces, or derived quantity. If you continue with this and we say, look, this is to a point G over here, which is the center of mass of this object. This is an arbitrary axis. Its distance is r. Ix is just going to be y squared plus z squared, which is really y prime plus yg, the distance to the center of mass, z prime plus zg, quantity squared, and these two quantities go to 0. The remaining terms are left. This becomes an r squared, which is the distance to the point of interest, and you're set. Now, if you do this as an arbitrary shape, and it doesn't matter that I can't draw 3D, but you could imagine it in any direction, rotated about here, the distance from the perpendicular distance from AA prime to BB prime is just going to be D, and I about, say, axis A is just IG plus MD squared. When you have thin plates, which is a common case here, we can have a number of different axes that we look at. And in that case, for a thin plate of uniform thickness, which is T, and homogeneous material density, which is rho, and the mass moment of inertia with respect to that axis, which is here defined as AA prime, is going to be r squared dm. And so if I do that, I want to have it as an area integral, so I can say density of material, kilograms per meter cubed, times thickness, meter, and so then I have r squared dA, and that's my meter squared. So out of that, I'll get rho Ti AA prime. You'll notice that this units are different because they don't include directly the moment of inertia in there. So it would be combined to get the mass moment of inertia. And you see the same thing over here, IBB prime area. So that's the only difference here. Difference in terms of the axes. Of course, the numerical values in both of these cases will be different. Finally, if I do a normal axis through the plate, I end up with ICC prime, and that's just going to be rho T times the individual area moments of inertia, and which is the mass moment of inertia is added up together. So that's kind of a useful relationship too. So the most important sort of relationships we can deal with sort of larger 3D objects are things like thin plates, principal centroidal motion axes on a rectangular plate. So we have here AA prime, BB prime, CC prime, same sort of thing. IAA prime is 1/12 MA squared. A is this distance right here. IBB is going to be 1/12 MB squared, and about C prime it's 1/12 M A squared plus B squared. And you can see that everything depends on distance, the normal distance with respect to that axis, and that's why you have these different results in all three directions. Same thing with the centroidal axes, but here, because it's symmetric, and that's not because of my drawing, this R is R all the way through, and it's that C is at the center. IA prime equals ABP prime, which is 1/4 MR squared, and ICC prime is equal to 1/2 MR squared, which is one of those things that you really should memorize, yeah, or have on your crib sheet. And if for some reason the exams are open book, you still should have a crib sheet that you create for this course. Finally, we have moments of inertia of a 3D body by integration. So here, I've just sort of taken, say, a parabola, rotated it around, and its elemental distance can be, or elemental mass element can be defined as rho density pi r squared dx. Here, I'm just defining things in terms of disks. So you see here at the very bottom a disk of thickness T. If I integrate 1/2 r squared dm, substitute dm into here, I get dix, diy, diz. And these are the three values that I'll get along each of the axes that I'm interested in. You could do the same thing with disks and shells. So you could, instead of doing a disk, you would integrate interior shells. So you just sort of stack this up. It's like one of the children's toy I had when I was a kid. And if you do that, you just change this one. So it's the difference between the two areas and you integrate across. What's important out of this, and you don't often look at these that much beyond there, this one is important. You need to know thin rods. You should know this one right here, the thin-walled hollow cylinder, and you should recognize that that is the equivalent to a radius of gyration. And so the goal with the radius of gyration is essentially to create a thin-walled hollow cylinder with all of the mass equidistant from the axes of interest. Thin rod, 1/12 ml squared. That's one you really need to know. Solid circular plate, something you really need to know. Hollow plate, sure, that's a good one. The rest of them are not as important. No, the rest of them are not as important to memorize. These are ones you should be aware of, and if you are aware of them, you should be able to recognize when to use them. You are not expected usually to memorize, say, for example, even the solid sphere or the hollow sphere. This is typically engineers look up tables, and nowadays they don't even look up tables. They just either brute force integrate these values, or they have references. So if you look at MATLAB, Octave, or various other ANSYS, you'll have a lot of software packages that pre-build all of this information directly in there. You know a lot of these things, especially for area moments of inertia from Civ 100. However, it's really good to have this sort of lecture where you're talking about the mass moment of inertia, just to get comfortable with the idea, and also to look at ways of calculating them. And this is really something that is helpful as you're sort of going through this course, is recognize where this is derived, despite the fact that often you don't do the derivation yourself in this course. Later on you will, and especially as you go towards third, fourth year. If you model these, if you analyze them, you do anything, you should really know where it's coming from in order to properly apply them.